All right. Good morning or good afternoon, ladies and gentlemen, from wherever you're joining us in the world right now. Welcome to this Synera partnership webinar together with our partner Rafinex, where we will discuss sustainability at scale in the automotive industry with focus on robust topology optimization. As the automotive industry evolves towards e-mobility, there's an ever-increasing need for a step change improvement in efficiency and weight reduction to counterbalance the mass of battery packs, making topology optimization ever more important in shaping the vehicles of the future. Stochastic topology optimization improves automotive components' safety and performance by creating lightweight designs that have formally robust and durable components. As for the agenda, I will first introduce the speakers for today's session before we walk you through the mission and vision of Synera. Andrew will then announce the partnership with Rafinex, followed by Andre giving you an introduction to stochastic topology optimization. This whole webinar is then topped off with a demo inside of Synera that Andrew and Andre will be walking you through. At the end, we will have time to cover all your questions in a 15-minute dedicated Q&A session. So please put all your questions in the chat box or the Q&A section inside of Zoom. I'm thrilled to do this webinar with two experts today, namely my colleague Andrew Sartorelli from Synera and the CEO and founder of Rafinex, namely Andre Wilmes. Andre, please introduce yourself to the audience.
Well, thanks, Yusuf, for having me, and thank you, ladies and gentlemen, for joining us today. Yeah, my name is Andre Wilmes. I have a background in aerospace engineering and numerical methods, and I'm the CEO and founder of Rafinex today. I am joining you from Luxembourg, although my team is currently distributed most all over Europe. It's a pleasure to be here today.
Thank you, Andre. Really excited to have you in today's session. Andrew, if you want to go next.
Hi, Yusuf. It's a pleasure to be here today representing Synera. Being able to announce one of our new partnerships is really a pleasure for me. I spent the last decade or so working at various engineering software companies, and it's always exciting to be able to bring forth the fruits of labor and share a bit of what we're doing with our customers.
Excellent. Really looking forward to the session today, guys. All right, a little bit about Synera and how product development processes have been done in the past. So for hundreds of years, engineers focused on developing parts and accepted the fact that they need to invest their manual work and labor in form of money of the company in the development of every single part. And this happened repeatedly. With every new generation of a part, engineers start development again, basically from scratch. This was true in the past when we engineers used pencils to draw on papers, and this is still true today when engineers use, for example, CAD and FEM systems to digitally, quote unquote, draw or create a digital file. The tools evolved, however, the working principles did not. In the future that we see with Synera, and even today, we see that engineers can and will stop developing the part and will start developing the process. This saves an enormous amount of resources because we engineers can recycle the process in case boundary conditions or other requirements change. Our vision is to focus on the connection between invested, manual work and created value, which ultimately translates into ROI, such as saved time and money. Simply said, in our world, engineers accept the fact that they create things which drastically lose value over time, and at the same time, they accept the fact that mistakes are made more than once. And that very moment when engineers start to create the process itself, they create value, which will survive over time. Even more, every time a new engineer opens a workflow in Synera and works on it, new ideas are added. Thus, more efficiency is added on top. Processes are stored, saved, and remain accessible to every new user of the workflow, which makes communication and collaboration much more accessible and seamless than ever before. Engineers are wasting over 80% of their daily time with repetitive work caused by rigid product development processes. To overcome this, and as already alluded to a couple of minutes ago, Synera empowers these engineers with the power of visual programming to eliminate all the repetitive work they are doing today and to give them all the time to concentrate on better products and develop them even faster and in a more streamlined manner. Synera, in a nutshell, connects different CAD and FEA and CAM tools together, so one platform to rule them all. This allows you to create processes where the information streams from the requirement management to the CAD or even the FEA tool over to the preparation of the manufacturing processes, all in one user interface, which will also be demoed for this particular use case today, later on by Andrew and Andre. On average, our customers already achieve a time reduction of 76%, which is spectacular. And with that, I'm now handing over to Andrew.
Thanks, Joseph. One of the pleasures being the software partnership manager here at Synera is being able to announce the partnership between Synera and today Rafinex. There's been a lot of hard work on both sides going into creating this connection between our two softwares to really enable engineers to effortlessly automate their design and automation processes with the help of next generation stochastic topology optimization algorithms, thanks to Rafinex. I'm going to get a chance in a few minutes to share with everyone a quick demo of the workflow that's possible now thanks to this connection. But first, I'm going to let Andre, the founder of Rafinex, share a bit about the strength of this technology and how it's solving problems in the automotive space today.
Indeed, thanks, Andrew. I can only echo the pleasure it's been. Not only are we breaking ground here on CA technology, but also on computer and software integration. So it's been quite a pleasure to work together. Now, before we jump into the meat of things, a few words maybe on who Rafinex is. Some of you may have heard of us, some of you may not have so far. So Rafinex is really an algorithm development company that's specialized in advanced optimization algorithms with a point know-how in uncertainty quantifications. So in and around how do we make CE tools more realistic, more reflective of the real world, and also being able to compute business risk for the end users and the end customers. Now, technically, we are a spin out of a kind of renowned German institute out of Berlin, the Weierstrass Institute for Applied Analysis and Stochastics. But nowadays, as I already hinted at, we are headquartered in Luxembourg, but my team is spread all over from the Czech Republic, over Germany, over the UK, London, sometimes even Portugal. So we are a digital, ground-up European outfit focused on high-quality mathematics and high-quality algorithms. So fundamentally, the problem Rafinex is tackling with stochastic or robust design optimization is over-engineering. The cost of bad design. People spend millions in process manufacturing, technology, quality control on materials, all of which are valid undertakings. But if the underlying design shape, which is locked in very early in a product's life cycle, is badly chosen, quite a substantial amount of money and cost is left on the table. Estimates vary, but somewhere around 70% of a product's life cycle costs are locked in during ideation phase already. So the ability to optimize very, very early on, even sometimes when requirements are not fully known yet, and we'll get to that in a second, are really mission critical for the future of resource efficient engineering, particularly if business models are changing more and more to manufacturers actually owning the fleet of their products after they've been manufactured. And then suffice to say, with the recent energy and material cost problems and geopolitical implications, this problem has just become much, much more time acute. So ultimately, design optimization is always a trade-off between time, money, and risk and cost. So design optimization was and has been possible in the past, but the question was always how much human resource time, compute resource time am I willing to invest, and what happens to my residual risk? Now, what we have achieved at Rafinex is that we have taken classical topology optimization and we have augmented it with real-life data, also formerly known as uncertainty quantification, which makes the algorithms slightly more complicated, just as an understatement, but which also bring in the fact that now you can optimize very swiftly for formally robust parts, which are optimal under nominal conditions, but retain a certain amount of performance, safety, and reliability under off-design conditions. So that is critically important for business end-to-end cost, go-to-market speed, and managing business risk associated with the rollout of your products. And this is what we formally refer to as robust optimization or robust optimization tradecraft. So this is an example of a kind of simple but very intuitive to understand example of the differences between a standard optimization and a robust optimization. So if we look at the lower left, so under an idealized load, then under a uniaxial load, the perfect solution is a pylon. However, if we just allow this inbound load to fluctuate a little bit, then a multi-pod or multi-leg is the better solution. So it kind of makes sense that we are sitting on multi-leg chairs and we're not sitting on top of a Segway. So that is kind of conceptually the difference between a classical optimization and a robust optimization. For the specialists in the room, when we think about solution spaces, then effectively robust optimization aims to find the highest plateau in a solution space rather than the absolute highest peak in this mountain range. And again, the business implications are in around safety and reliability of the product in service. So ultimately, this leads us under variability. So if you optimize with variable input parameters, and these can be the loads, they can be the material properties, you find new shapes, formally robust shapes, which don't come spectacular, unfortunately. So we're not talking about coral reef looking geometries, but we're looking at geometries which are trained mechanical engineer or aerospace engineers. They look at these parts and you go, okay, ambitious, but sensible. I can understand how this part does its job. So all the shapes that you see here today, none of them have been filtered, none of them have been smoothened. All of the geometries you see today are actual FEM computed and then manufactured parts. So common features in these robust geometries are U-channels, T-beams. Something that we're rather proud about is the occurrence of shell structures during topology optimization, which is rather rare with classical tools. And all of this results in geometries which typically have quite high modal frequencies and robust stiffness properties as well. So just a word before we jump into the demo, the kind of end-to-end workflow of the Rafinex technology starts really at the design space. So the maximum envelope that your geometry can sit in. So as a first off, what we do is we do a fully automated TED10, so second order analysis on the design space. Why? It allows you to quickly learn about your project or your problem setup, and it shows you which are the worst load cases, what kind of drives your problem setups, and it gives you the upper bounds of what is achievable. Because filling the design space with 100% material will give you the highest kind of upper limit of what's achievable in terms of stiffness performance. Subsequently, in the next step, we then do a stochastic topology optimization with adaptive meshing on the fly, resulting in very high resolution, very well defined, and always continuous shapes. So we do not suffer from islands or kind of satellite sticking away beams looking structures. So we always have a smooth surface, which we can then automatically post-process or hand over to, again, a TED10 second order stress analysis, so that we effectively get the engineer from design space to reliable, formally robust geometry that is fully digitally validated, so that end users or engineers can get to a state that they can make quick, informed decisions on the basis of reliable FEA validation and analysis. So this is about 10 times faster in terms of workflow already than most status quo implementations in the market. And most of this technology we owe to the usage also of adaptive remeshing during optimization. So we've taken this technology, we spent a few years maturing it with automotive OEMs before even launching our product. So in about late 2021, we then took this technology and built it into a fully fledged cloud-based CA software tool that we then nicknamed or labeled Möbius. So this is an API-based, cloud browser-based software that is fully secure with ISO 27001 certification, and it exposes or it provides these capabilities for next-gen stochastic topology optimization to our customers, but then now also to our partners such as Synera. Okay, that brings it to you, Andrew.
So it's my pleasure today to get a chance to show everyone a bit of the Rafinex connector for Synera. One of the great things that we've done here is take a lot of the capabilities that exist within the Mobius product and make them accessible through Synera. So directly using that cloud API to securely send all of the information between Synera and the Rafinex Mobius product. Whether we're doing the automated optimization or design validation processes after the optimization process, it's all possible now within the Synera platform. Coming soon is even the option to optimize using IoT data, thanks to our MQTT connector, which allows for sending this data back and forth between Synera and, of course, the amazing stochastic loads are accessible through the Synera platform. So now I'm going to jump into Synera and give everyone a quick overview of what's possible now. So for those of you that haven't seen Synera before, here you can see the low-code environment. On the left-hand side, we have the canvas, which allows us to add and remove nodes and construct our workflows. And on the right-hand side, we have the viewport, which really enables you to interactively view those results from your visual programming workflows. In this case here, starting out on the left-hand side, we can actually see some of the new nodes that come thanks to the Rafinex add-in. So we have, again, the ability to generate meshes directly on the cloud and stored with our model there without anything leaving the Rafinex platform. We have the solver to allow for validation of the original design space or even the optimized shape after the optimization process. Of course, we have the Mobius optimizer, allowing you to send your models to be topology optimized there. And then we have the stochastic loading here, allowing you to take advantage of that really unique possibility. But let's see this in action. So you can actually see on the right-hand side, I've got the part that I've already optimized here. We can see this nice structure, and let's see how we got there. So like most workflows inside Synera, this one starts out by importing some geometry. In this case, we're directly importing a parasolid file. Synera has access to a lot of the leading CAD kernels and translators there. So whatever CAD tool you're using, we're going to be able to bring in some of that geometry. Or I also need to bring in a few other items from outside tools. So we're going to, in this case, take in our isotropic material. We've just entered the values that we wanted here. And we also have some loads and boundary conditions that we've set up. Of course, doing an optimization process, doing finite element analysis, we need our loads and boundary conditions. And here you can see in the visual environment, we've set up some different loads that are going to be applied to our component here. Now, in this case, these are fixed loads that we've specified here, but in the future, you can imagine we can actually replace some of these inputs thanks to our connection to MQTT and read in some of that nice IoT data. Now, once we've set up our loads and boundary conditions, we're going to go ahead and we're going to start to construct our model. In this case, we can now see the model that's been uploaded to the Rafinex servers. We can see the different surfaces there where we've applied different loads and boundary conditions colorized differently. The next step in any optimization or analysis process, right, is going to be generating a mesh. So we can see here this really nice full tet mesh that we've generated, again, fully on the cloud without leaving Rafinex servers. And the first step in our process, right, before we even get to the stage of optimizing this part, we want to understand the performance of it to start with. And so we're going to take advantage of that built-in validation server where we've selected, okay, we're going to run this analysis on our initial design space. You can see we get out some information about the maximum displacement, von Mises stress. We could even scroll up a little bit here and see the stiffness the part for different load cases. It's going to be really useful when we go back and look at the optimized part and want to compare the results that we've generated. So the next step in the process, right, is we're going to actually run the optimization. And now we can see this nice geometry that we've got back, really smooth results. I have to say, I've been working in the engineering software space for a while, and these are really nice results coming out of topology optimization here. So kudos to Andre and team. And of course, the next step here is going to be validating this geometry after we've optimized it. Now we can see the validated geometry. We've gone ahead and run a post-optimization validation here on this using the loads and boundary conditions that we'd already specified. A really nice feature of the Rafinex solver here. And again, results stream back directly into Synera. But again, I said the nice thing here is we can actually go ahead and take a look and compare our stiffnesses before and after, thanks to this nice addition here. So we can see actually stiffness reduced in both of our load cases, but also a little bit difference on the maximum displacements here. So really a nice optimization done by Rafinex. Of course, once we go ahead and optimize this part, most workflows we're going to have to go ahead and actually turn this back into CAD geometry. And this is really where Synera comes into play, where we can generate a quad mesh of our part using some of the built-in algorithms for Synera. And then we're going to actually convert that quad mesh into a nice BREP geometry. Because we do have the power solid kernel inside Synera, we're able to do those nice BREP operations. We're going to do some Booleans to actually end up with our final geometry here. And we can see we've actually been able to add back in some of those functional faces, functional surfaces that we're going to need for mating and other things. Maybe if we're doing a further multi-body simulation with this part in, we're going to need to mate those surfaces in for those contacts. Now, I've been told coming in the future here is actually going to be a direct link to export your Nastran bulk data file from Rafinex. So when we want to take this into a validation actually inside Synera, pretty soon we'll have that direct connection there to make it even easier, whether you're using Autodesk Nastran, NX Nastran, or MSC Nastran. So now once we've got this geometry, we've got a few different things that we can do here. As I said, we could do a further finite element analysis, or we're going to jump down here and actually we're going to take a look and we're going to mesh this part and use one of the add-ins from another one of our partners, Fraunhofer IAPT, to do a costing analysis on this part. So because this is a cast geometry, we can go in and say, okay, we want to have this many parts in our batch, and we're going to specify a few different material parameters where you can specify the price of the material, the density, so on. It really gets quite elaborate here, but in the end, we can actually see what is a projected cost. So maybe if I'm going to go ahead and turn this into, I don't know, we're actually going to go into really high serialized production. We can see the total cost for this, and again, the unit price there and different costs for various aspects of the manufacturing operation. A really nice thing to kind of complete the workflow, not just optimizing for performance, but also optimizing for costs. And again, the other step we could take here, if we wanted to, going ahead and generating an FE mesh that we'll use for running this analysis. I'm not going to go into too much detail here, but again, the nice part about Synera is we really give you a lot of options. So once you construct that workflow, you have the option to use whatever solver that you want. So whether you're doing a nonlinear analysis or linear analysis, you can simply plug in, if you're an ANSYS user, if you're a Nastran user, whatever flavor of Nastran you're most comfortable with, Abacus, OptiStruct. We have options there for all of them to really allow you to tailor this workflow to your needs, or maybe the needs of the partner that you're working with, or the company that you're doing a contract for, so that you don't need to recreate your entire process from scratch just because you're switching solvers around. And again, in the end, we end up with this nice optimized geometry, and we can simply take a look at the results in the viewport here. So that really concludes the quick demo of the new edition of Rafinex Mobius optimization technology connected inside Synera, as well as the Synera platform. And now I'm going to hand it back to Andre.
Yeah, thanks, Andrew, for the very good overview. So yeah, I'm very excited to be able to provide our technology in like a full end-to-end data information environment, let's say, of OEM customers, and provide it in even further extended workflows.